All right, so we're going to start today. Oh, no. Okay, can I extract this without disconnecting my camera again? Yes. Okay, so we're going to start today with sort of a spare part theorem that turns out to be really important. Well, I mean, spare part in the sense that I left it behind. Remember, the last class was really about, obviously, the last class was really about the theory of integrating complex functions, right? And so a lot of the sort of structural theorems about how complex functions really behave we left behind in our pursuit of teaching you everything there is to know about complex integration, which of course we didn't, because if you took a second complex analysis course from somebody like Professor Camp or Professor Lin, you would get way more contour integration piled into the mix. Because the way this stuff is used in practice is even more technical than what we did. But those of you that have been thinking about problem 7 may have at least two separate groups of you guys were wrestling with the weirdness of trying to crush the entire complex plane into like a tight neighborhood around a point, right? If you really thought about what's going on in that question, it's an odd thing to think about, especially if somehow it's going to preserve like right angles, right? You're going to feed it curves that are at right angles, and somehow you're going to crush the entire the entire complex plane at the unit disk, and the difficulty in doing so. And the reason it doesn't work is because of a theorem called Liouville's theorem. So that's what we're going to start with today. Liouville's theorem is like a counterexample generator. And so for just a brief moment, we're going to drift back into math that looks like 410. And we're going to arrive at a theorem that actually is how you prove the fundamental theorem of algebra, the sort of classical way of doing it. So where am I allowed to write here? All the way over to here. Okay, so we're going to start with a theorem called, here we go. Here is a quiz for you. What was the Cauchy integral theorem for derivatives? Cauchy integral theorem for derivatives. What did that actually say? Okay, there's definitely an integral involved. Okay. Is there an F? Well, let's just locate it at a particular point this time, right? N plus 1 dz. And there was some adjustment factor out front. N factorial, the usual 2 pi I, and what was all that nonsense equal to? The nth derivative of f evaluated at z0. And usually what we do is we would assume that we're talking about some sort of little circle around the point that we were talking about, right? The idea here is that you have some z0, you have some circle that wraps around it. This is supposed to be in the middle. Adjust it. So, because of the circle contour theorem, you're always allowed to reduce it to this, right? The case where you're wrapping around some little circle, say of radius r, and that this theorem generally held. All this is doing is picking out the coefficients of the Taylor series, right? This is essentially the idea of this theorem. So, you can use this to prove something, to prove a family of estimates called the Cauchy estimates. So, we're going to build up to, the idea here is that we want to prove a theorem about functions that are bounded and entire. So we're going to be working with entire functions. So remind me what an entire function is. Analytic everywhere, right? So the word entire meant analytic on all of C. And in particular, it means that we've got a power series on C, right? We have a power series for the function, that power series converges for every value of x. Okay? So can you give me an entire function on R? E to the x, that's a great one, right? So it's okay to be entire on the reals and also the complex, like there's real entire functions and complex entire functions. So, and then of course by the extension theorem, if you're entire, there's a good question for you. If you're entire on the reals, are you automatically entire on the complex plane? Yes. Why? Okay. See, I shouldn't have said extension theorem because I gave the game away, right? Yeah, same radius of convergence. So because you compute it with the ratio test, essentially, is what's going on with the extension theorem. So, e to the x, which is x to the n over n factorial, that converges for any x that you plug into it, right? This is legit on, the way you learn it in calculus is r is equal to infinity, where r is the radius of convergence. Any others that you can think of? Like 4 examples from calculus 3. E to the x, sine x, cosine x. And then the one we just flogged the hell out of last quarter, which was the geometric series one, right? 1 over 1 minus x, which is not entire. But sine x, we'll just put down one example here, minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. This also is entire. This function is unbounded, because the graph of e to the x races off to infinity. This function is bounded. Sine of x oscillates back and forth between minus 1 and 1. So this is a bounded function. When I talk about a function being bounded, I mean that there's some... I mean on R. These things are unbounded and bounded on R. As entire, considered as functions on R, this is unbounded, and this is bounded. So, and anything you construct out of a finite number of bounded functions will continue to be bounded. And you can construct like infinite sums of bounded functions, and they could potentially continue to be bounded, depending on how you can like add the functions together. But the idea is this is not unusual in R. It's not unusual to have a power series that oscillates forever. If you haven't seen the definition of bounded before or in a while, I already run off the side of the board. Okay, this is mine. Do not go past this line for the video. What I mean by bounded in a more technical sense is that there exists an m, so some real number, positive real number m, such that f of x in absolute value is less than m for all x in R. So that's sort of technical definition of bounded. I can find some to get better gear. Okay. So the idea is that what this m is doing is sort of trapping the function in absolute value, right? You can't go above m, and you also can't go below m. And the idea with complex functions, and this is really weird, is that this case can't happen in the complex plane. You cannot have a function that's defined by a power series that converges everywhere that doesn't race away to infinity. So all class of things, like even sine, like sine is an entire function by the extension theorem. You could put z's in here and put in any complex number you want, and this thing will still converge. But the function, you can't draw any circle beyond which, there's no bound you can put on the function. So it will run away to infinity as you get away from the real line. So what I mean here is, if you haven't thought about what the sine does, we just briefly talked about this in the last class. And I showed some of you guys, I think, a picture of it in one of the work sessions last quarter, is that if you have, say, the sine function, so imagine this is modulus of f of z up here, and here's your real line over here, and here's your imaginary line over here. If you plotted the sine restricted to the real line, it looks like the real sine function. If you just feed it sine or like x's, real x's, what is happening is you end up with, restricted to the real line, you end up with the sine function. So on the real line, the sine function is actually just doing what it does. Oscillates up and down. Presuming I've drawn sine correctly there. The thing is, and some of you were listening when I started the class today, if you actually write down sine z, well, sine z has an e to the iz inside of it and an e to the minus iz inside of it. Not e to the ix, where x is some real number, but e to the I complex number z. And so this thing is, so anything that looks like e to the iz is e to the ix plus iy, which is e to the ix times e to the minus y. This is a real valued thing. And it's a real valued thing that if you put in big negative values of y, this runs away to, this is trapped between, on the unit circle, right? These are unimodular numbers. That part lives on the unit circle. That part can race away to infinity. So even though the sine is bounded when you restrict it to real numbers, what's ends up, I can't even draw this, because what happens is the sign sort of spreads out in this sheet that in modulus now, right? So there's so this isn't really the modulus of f of z. It's hard to draw f of z. What's ended up happening here, I'll fix it. There's the modulus of f of z. Right, so sign kind of lumps like this. In modulus, what happens away from the real line, and this thing must sail away to infinity in absolute value because that thing is running away to infinity. If you put in big minus values of y, you go to infinity in this term. And if you put in big positive values of y, you go to infinity in that term in modulus. So these things get huge as you go away to infinity. And this is the general behavior. If you have a power series that converges everywhere for a complex number, it will always have this behavior where it sails away to infinity in modulus. And that's the content of a theorem called Liouville's theorem. So, why does that hold? This is an important enough idea that I should show you because we spent all that time in 410 working on things like fn at z naught is equal to n factorial over 2 pi I times the integral over some contour of f of z over z minus z naught n plus 1 dz. So there's a theorem that says, well, I mean, that's generally true. So imagine that you were on some little circle around z naught. So here's z naught. You're on some circle of radius r. So that your distance as you wrap around that circle would be, so the length of this curve, length of c, would be equal to 2 pi r, right? Circumference of that little circle is 2 pi r. And if you assume that f is bounded, if you assume that f is a bounded function on some domain, A containing that circle so you imagine that there's some set that sits around this called A, where the function is analytic and bounded. So f is bounded, which is assuming an analytic f, is bounded on this domain containing the circle, then that means that the absolute value of f of z must be less than m when restricted to that circle, right? There's going to be some point on the circle, there's not some point on the circle. As f travels around the circle, it must be smaller than m. If f is bounded on A, certainly it's bounded on the circle by the same bound, yeah?
And it can't be equal to the bound because of the
Maximum modulus principle. It's not going to be equal to the bound on all of A, but it will certainly have some maximum modulus that will occur on the circle. Okay, so now we just apply the ML inequality. Remember the ML inequality, to remind you guys, this has been a billion years since you've done this, is a way of estimating the size of an integral by hitting it with absolute value signs. So if we have this setup where f of z in absolute value is less than m, we have the circle sitting inside of A, so the function is analytic, then I could say that the absolute value of the nth derivative of f at z naught is equal to the absolute value of n factorial over 2 pi I times the integral of f of z over z minus z naught to the n plus 1 dz. But if we restrict ourselves to the circle, z minus z naught is a point on the circle. I know the distance from z to z naught. It's r. Every one of these points is on the circle that we're talking about. So z minus z naught just leaves behind r. Right? And that's how you define a circle. I know I'm reminding people of a lot of stuff here, but remember that that circle is parameterized as z is equal to z naught plus e to the I plus r e to the it. That's the standard parameterization of a circle. So z minus z naught is just r e to the it. Okay, so all this stuff turns out to be less than or... Oh my gosh, it didn't break. Okay, that's good. Less than or equal to n factorial over 2 pi. The I disappears because we're taking absolute values now. And what the ML inequality says is that we can replace the value of this function in here, we can replace the integral with the maximum value of this function times the length of the curve that we integrated around. It's the standard, like replacing an integral with a rectangle idea. So what is the size of that function? It is m over r to the n plus 1 times, that's the bound for f of z over z minus z naught, times the length of the curve that we integrated around, which is 2 pi r. And so this move right here, this is the ML inequality. And again, if you're confused by that, just remember that it's really just replacing the integral by that old rectangle thing, where find the highest value of f and make that the height of the rectangle and just multiply by how far you went across the bottom. Well, that means that we can simplify this to get that this is less than or equal to k factorial over r to the n times n. And this family of inequalities here, where all I did here was I just canceled the 2 pi's and I canceled the r's. What you arrive at is something called the Cauchy inequalities. So the Cauchy inequalities say that if f is analytic and bounded on A by M, and C is a circle of radius r centered at z naught, contained inside of the domain A, then the nth derivative of f at z naught is, in absolute value, is less than or equal to n factorial over r to the n times f. It's pretty weird, actually, because it means, qualitatively what this means, is that an analytic function has very, an analytic function has very tight controls over how fast its derivatives can grow. So as soon as you say something is analytic, it means it just has limits on how steep it can get. Okay, now, it may not be obvious at all how this is going to lead to Liouville's theorem. Because what we're going to do is we're going to say this fact right here, the fact that the derivatives, remember these are the derivatives, that the derivatives of f are bounded on circles is somehow going to turn entire functions into bounded functions. So the next part of this proof is not technical at all. This is the most technical thing we'll do today. Might be the most technical thing we do all course. So let's see what would happen if we do the following. So let's let f be entire. So that is, we're going to say that this holds on all of C. F is entire. So we'll let f be an entire function. And we're going to let f be bounded on all of C. So that is, there's a single constant m that works in every one of these inequalities. That is, the absolute value of f of z is less than m, or z naught is less than this m for all z and c. Well, I can pick any circle of any radius I want to invoke this argument with, right? So let's just pick, we're sitting in the complex plane, we pick any z naught we want, we draw a circle around it of radius r. Well, it seems like we can invoke this theorem. Maybe we should invoke this theorem on the first derivative to see what comes out. Hopefully you guys agree with me that we've got the setup for applying the Cauchy inequalities here, right? Because that circle is in the set on which the function is analytic. The bound is universal. And so if we apply this inequality with n is equal to 1, what we end up with is, so now apply this fact with n equals 1. And what that says is on that circle, so on that circle, we get that f prime of z naught is less than m over r. I think that's what it says, right? It's r to the first. There's no factorials running around. But that holds for every circle. Every circle of every radius is contained in the domain on which this function is analytic. So what happens if I let the circles get bigger and bigger and bigger and bigger and bigger? If we let the circles go to infinite size, every circle is in the domain of the function. The bound holds on every one of those circles, and so this inequality holds for every radius. So if you let r go to infinity, that means that the absolute value of the derivative of f must be equal to 0, because this fact is true for all r. Well, that means, what's the only number that has modulus 0? 0. So if the modulus of the derivative is 0 at z naught, then that must mean the actual derivative at z naught is equal to 0. But f is entire. I could make this argument for every z naught, every single z naught in the complex plane. This same argument works for, because f is defined and analytic at every z naught in the complex plane. This holds for all z. So if I have a function whose derivative at every single point is equal to 0, then what is the derivative of the function? 0, right? If a function is equal to 0 everywhere, it is 0. That's the definition of the 0 function, right? It takes literally every input to nothing. So f prime of z naught of z is equal to 0. It's identically the 0 function. And what's the integral of the 0 function? Constant. So f of z is equal to 0. We know the antiderivative exists here because f is analytic on everything. Analytic functions have antiderivatives. We just did it. For some z. So f of z is a constant function. So this bizarre technical estimate on the growth of the derivatives of f ends up giving you this incredibly powerful theorem called Liouville's theorem that says any entire bounded function is necessarily a constant function. This gets used all the time when we're talking about like analyzing what can happen with complex functions and what can't. So even if you don't remember any of the technical details about why this is true, I mean, it's a useful thing if you're working with analysis to know this is what's going on here, that you've got this function where the behavior must be controlled, but since it must be controlled for all circles of all radii, it sort of forces the behavior of f. If you want to remember anything, there may be other questions that show up in this class where this is going to be invoked, right? If you see a function defined on all of C, you should get suspicious. Maybe this is running around in the background. This is the way it comes up. So, entire function that is also bounded must be constant. So now let's talk about homework question 7. Questions about this so far? Okay, I know this has the flavor of 410. Occasionally we'll have to do something like this where we get down into the... Somebody in my office the other day was like, it doesn't seem like we're doing anything from 410 so far. Well, there you go. There's your piece. I hope you enjoyed it. Okay, so what am I asking you? What am I asking you in question 7? I'm saying, is it possible to come up with either a one-to-one onto function, so bijection? Is there a bijection a conformal bijection between the disk and the complex plane? Can I find a conformal bijection? Which is also asking, equivalently, could I find such an object from C into D? Now, logically, these things are equivalent, right? Logically, they're equivalent, but oftentimes one direction of a question is easier to think about than the other direction. So, one of these cases you can immediately apply this idea to. Let's suppose that we had such an object. Suppose that you had an analytic function that took C into D. Suppose, now the reason why would I pick this case and not that one, because if a function is defined on all of C, then it's entire. Right? The analytic function's on all of C, it's an entire function. So I'm going to pick this case to analyze, because if I could get from C into D, I would be talking about an entire function. And entire functions have very strict controls over what they can do. Okay? Well, suppose there exists an F, conformal, and one-to-one. We don't even need the one-to-one and onto. Just suppose there exists an F that was conformal from C to D. What would that mean? What does it mean if the outputs of a function are all stuck inside of a disk of finite radius? It's a bounded function, right? The outputs, if this was possible, if I could take every complex number and feed it into a disk, that's what it means to be bounded. You can draw a circle around the outputs and it can't get outside that circle. So if this existed, it would be a bounded function. So if you had a conformal map from the complex plane into the disk, then it's actually bounded in modulus by 1. Then F would be bounded. Wait a second. It's an entire function because it's analytic on all of C. It's a bounded function because the outputs go into the disk. And so therefore, what kind of function is it? So the only such functions would be constant functions. The only function that can do this is a constant function. So F must be constant. I don't know about you, but I don't think of constant functions as being one-to-one. Right? Everything to one. So, can there exist a one-to-one onto function from C into D that's analytic? And the answer is no. The only functions that can do this are constant functions, and those are badly not one-to-one, nor onto. Not one-to-one. The question asks, can you find a one-to-one and onto function from C to D? The flip of that question says, well, okay, well that direction sucked. I mean, it didn't suck, it just can't happen. So we can't go from C to D. Can we go backwards? Now, if I don't include the condition that the map has to be an onto map, you can just use the identity map, right? I mean, f of the disk, if f of z is equal to z, f of the disk is just the disk, right? So that's a one-to-one map into C. Maybe you guys haven't come across this stuff before. If I do this, but I take the function f of z is equal to z, and I take the disk and I put it into the complex plane, what I mean is that the output lives as a subset of the complex plane, but it's not equal to the complex plane. So in the case where I don't use the word onto, but instead I say into, I mean subset. If I say onto, I mean equals. Also, yeah, the words that are more typical here are surjective and injective. So an onto map is a surjective map, and a one-to-one map is an injective map. And if you've seen any category theory, then maybe you've seen the word meromorphism and epimorphism before, but God help you. Okay. So, what if one of these existed? What if we found one? What if we found an analytic map from D to C. Well, it's not bounded, so that doesn't work. So if it's an analytic map from D to C, and it was bijective, which is what one-to-one and onto means. So if I could find such a map, I could find a bijective analytic map from the disk to the complex plane. If I could do that. If you know anything about bijections, you know already that this can't happen, right? But if you were going to say why, you would say, well, if you could do the other direction, then the inverse of this thing would also be a one-to-one onto analytic map in the other direction. If this existed, if you found an F that took the disk into the complex plane that was one-to-one and onto, then F inverse would take the complex plane onto the disk and would be one-to-one and onto. But you've already shown such a thing can exist. But this would be bounded and entire. So by Lewis' theorem, it would have to be constant. Okay. So your task is write that up in some sort of sensible way and get your head around what the logic is going on here. But the idea is really secretly in the background, as soon as you know that this can't happen, you can't invert it either, right? Conformal equivalence requires that you can get back and forth in an invertible way from set to set. And the upshot of it is something is qualitatively different between the disk and the complex plane. Some difference between them. And so remember that we talked about the Riemann mapping theorem said so the Riemann mapping theorem said that if A and B are simply connected and A and B are not equal to the complex plane, then A is conformally equivalent to B. So the upshot of this exercise is to show there is really some other class of domains running around, right? That you have one set of domains that are the sort of bounded, not even bounded, half-bounded even. Because half-planes fall into this category. So we've got two classes of simply connected sets. So far, we have things that look like circles are simply connected, and things that look like half planes are simply connected. That's one family. It's all these things where there's a boundary that cuts the plane into two sides, an inside and an outside. Right? So that's what you should think is one family of simply connected sets are sets with the domains that don't have holes in them, and they have a boundary that cuts the plane into two sides. And then we have this other family of these guys, which is everything, the whole complex plane. So those of you that were working on this question noticed that there was an issue with figuring out what to do with the boundary of these domains, right? And that's actually it really is the case that the boundary is the distinguishing feature between this type of simply connected domain and this type. So I'll point out there's actually one more kind if you're allowed to include the point at infinity. So let's do one last set here. What if, this is sort of an absurd example, what if I took a set like this, I took the boundary, and I look at the outside of the disk instead? Is that simply connected in C? Why not? Yeah, right? You can draw a loop here around this hole, and there's no way that you can contract that to a point without leaving the set, because you'd have to pull through the hole to do it, right? So This is not a simply connected set in C. Because that loop cannot be contracted to a point without pulling it through the hole. In fact, I guess the set we're thinking about here is the set modulus of Z bigger than 1. Right, so that it's like an annulus with infinity involved. What if I put the point of infinity in? So now imagine that instead of having nothing on the outside of the complex plane, that you have the brain-breaking idea that out here at the edge, there's this single point that sits outside the complex plane in every possible direction. So what about this set? So I'm going to draw the same picture. So I've got the circle. I'm looking at the stuff outside of the circle. But now imagine it's smeared around the outside of the complex plane, and I know this is hard to draw a picture of. Just imagine floating around out here is a single point called infinity. And no matter how you run off to infinity, you get to the same point. Remember, really, I'm going to draw the Riemann sphere in a second. I'm going to give the brain-breaking version of it first, and then make it clear what's happening with the Riemann sphere. Well, now if I drew this loop, and I said, can you contract that loop to a single point? The answer is, yeah, just let it all run out to infinity, right? Stretch it equally out to infinity every direction, and eventually all get there, so it can be contracted to the point of infinity. So here, in C union infinity, which is the extended complex plane, this is a simply connected set. This is simply connected. Now I'm presenting the point at infinity in a lot of different ways because when I learned this the first time, I was like, that's BS. There's no way that exists. It's nonsense. Why would anybody do that? It makes no sense. So in an effort to convince you, I don't know, I told some of you in the hallway the other day that one of the most famous mathematicians of the 20th century, this guy John von Neumann, is like the inventor of quantum physics and functional analysis and contemporary linear algebra, big pieces of group theory and matrix theory. He's basically a Gauss-level mathematician. Told some guy at a conference one time when he walked up to him and said he didn't understand something, famously, and possibly a apocryphal quote, young man, in mathematics you don't understand things, you just get used to them. So I'm going to just keep saying the point of infinity, you just get used to the idea that we just glom some point out there and you can reach it, you know, as a limited infinity, that those don't diverge anymore, they all converge to the same place, which is infinity. And the model that you can use to make it clear what's happening here, and I promise next week we're going to lay down what the Riemann sphere is concretely. The map of the Riemann sphere was the idea that you took the complex plane, that you had this sphere sitting on top of it like this, and that there was a one-to-one correspondence between points on the sphere and points on the plane by starting at the North Pole up here, and then you took a line, you took your point in the complex plane that you were trying to map to the sphere, and you just connect with a line segment, and wherever you cross through the sphere, as you go from the North Pole to the plane, that point is uniquely associated with this point. So it gets you back and forth. So every point in the complex plane has a line segment that runs through the sphere and connects it up to the North Pole. That point and that point are said to be in identification. Just we think about them as the same point. It's not like topological identification, we're rolling it together, but you know, this point and that point we can think of as being the same point. On the inside of the sphere, which is a good question, what happens on the inside? And the answer is the line segment goes through and then passes out the bottom of the sphere instead. So the bottom half of the sphere is the interior. The top half of the sphere measures what happens on the outside. Well, what happens to the North Pole? As you run out this way on the complex plane, the lines get steeper and steeper and steeper. So say you have a sequence of points running out to infinity. Well, the lines that pass through get steeper and steeper, and the points crawl up towards the North Pole. In any direction you go in the complex plane, as you run out further and further away from the origin, the lines crawl up the sphere, and that sequence looks like it's approaching the North Pole. So what we do is we say, oh, that's infinity up there. No matter how I left in the complex plane, towards infinity, if I look at the track that those points make on the sphere, they go like this. This sequence over here that runs this way, it tracks up. You can say, oh, okay, well, there's where its points are. They tend to the same point. And this is why we think of it as a one-point compactification. 1 point. No matter how I left in the plane, in the sphere, I approach the same point. There you go. You could still, again, my initial response to learning this was, this is BS. There's no way this could possibly work. But remember, you just have to get used to it. So why is this set simply connected? If you took that set, let's just suppose that you took the set where I'm going to draw a circle down here in the complex plane. So down here, I have a circle. And I have the Riemann sphere up here. So this circle in the complex plane, if you mapped where those points went in the sphere, they would make a circle that looks like this. And if you looked at the exterior of those points in the complex plane, I'm just redrawing this picture now. If you looked at the exterior of those points, those get mapped up here to the cap of the sphere. That, to me, looks like a simply connected set. If you draw any loop inside here, so you say, oh, look, I'm going to draw a loop. I cannot contract it to a point, except you can, because the image of that loop is this loop. And it's pretty clear that can be contracted to a point in the sphere, as long as you're allowed to use that point at infinity to pull it through. So there's no holes here, is the idea. So this is the third type of set that we see that is simply connected. So this type of set is simply connected in the sphere, or the extended complex plane. Then we have the type, the complex plane itself type, which is simply connected. And then we have the type that's the inside of disks, is the third type. If you're getting the sense that maybe topology is involved here in some sense, yes, this is one of the birthplaces of topology, is in thinking about these sets. So we've got disk-like sets. And that's going to be disks and half planes. We have C-like sets. C-like sets are going to be things like punctured planes, but it's all of C. I give you a challenge. How many C-like sets are there? It's just itself, right? It's just C. And then there's Riemann sphere disks and half planes. So it's outer disks, right? So annuli. So I should say Riemann sphere annuli. So sort of unbounded annuli are going to be simply connected in the Riemann sphere. These guys. These guys are like this. So it's one of the beautiful things about complex analysis is, unlike real analysis, where infinity is awful, you could just say, oh, there's no such thing as infinity. You just work with the reciprocal, and then you just work up here instead. So you can always get away with this. Yep.
Is a simple connectedness property true if we instead do a line at infinity and then do it in projective species?
Okay. So what do you mean by the simple connectedness property? Half planes.
Yes, the exact same setup.
So half planes are lines through. Oh yeah, this is another thing. I have to remind you guys, what does a line look like? It goes through the origin. In the complex plane, the line looks like this. So it goes through 0, and it also goes through infinity. What does it look like on the Riemann sphere? What does that look like? Well, it runs off to infinity, right? It goes through 0. So that means it must go through this point down here, because that's the image of 0. So 0 in the Riemann sphere lives down here at the south pole. Infinity lives up here at the top. So it's some kind of great circle. So lines in the complex plane turn into great circles in the Riemann sphere. And so half planes also turn out to have some sort of simple connectedness property. Yeah.
Oh, no, I was asking not about the Riemann spheres, but about projective space, so it's.
Let's talk about that later,
Sounds good.
if that's okay.
Sure.
So if you picked this and you took a half line here, you just color in half of the sphere instead, right? So you should be able to see here really secretly the reason that disks and half planes are the same type of thing is because that up here looks like a half plane. What we're going to talk about in the next part of the class is manipulations of the complex plane that are actually really secretly just rotations and contractions of the Riemann sphere. Okay, so yeah, you got both ends of the heavy mathematical stick today. You got the hyper technical intro and then the super vague pointed infinity hand waving at the end. So now that I've pulped you, finish up your homework over the weekend. I'm available to chat, and then I'll put some new questions up if you guys want to talk about if you want to work on some new stuff.
So is version around a circle equivalent to a rotation?